All right, so this is section 5.3 for business calculus, and this will be the last section that we cover for this course. And what we're going to talk about are definite integrals and area. So in this section, we're going to we begin this section by calculating areas under the curves, leading to a definition of what we call the definite integral of a function. So far, what we found when we found the integral of a function, we've found the function and then we've added a plus c. Well, that's the indefinite integral because it doesn't have that beginning, starting, and stopping point unless we have a word problem where we had a value to plug in for c. But what we're going to do now is we're going to integrate a function and then be able to calculate the actual number for it if we're given a starting and a stopping point. We're also going to talk about the fundamental theorem of integral calculus, and this provides an easier way to calculate definite integrals using the indefinite integrals. And then we're going to illustrate the wide variety of applications of definite integrals. Where is it useful? Why do we use it? All right, so we're going to start with the next slide. The diagram below shows a continuous, non-negative function, and we want to calculate the area under the curve and above the x-axis and between the vertical lines, so all this blue area. What we're going to be able to do and what we're going to learn in this section is how to actually tackle that. So we're going to begin by approximating the area by rectangles. In the graph below, the area under the curve is approximated by 5 rectangles with equal bases and with heights equal to the height of the curve at the left-hand edge of the rectangle. These are called left rectangles. If you did it where you were basing it off the right-hand side of the rectangle, those would be right triangles. Or rectangles, sorry. 5 rectangles, however, do not give a very accurate approximation for the area under the curve. Sorry, they underestimate the actual area by the small white spaces that are just above the rectangle. So that gives us, what these 5 rectangles do give us the area for each 5 of the rectangles, but we're missing out on this white area. So we don't have an accurate, we have an approximation, but it's not very accurate. So what if instead of 5 rectangles, we do more? Okay, and that's what the next slide shows. In the graph shown below on this slide 4, the same area is approximated by 50 rectangles. So we're going from 5 up to 50. And that gives a much better approximation. They still have the white area. Okay, it's just very, very small. Okay, and that's between the curve and the rectangles. And it's so small as to be almost invisible. So between the two diagrams, this suggests that if we have more rectangles, that gives a better approximation. In fact, the exact area under the curve is defined as the limit of the approximation as that number of rectangles approaches infinity. So as we get larger and larger and larger numbers of rectangles, eventually we'd have that exact area under that curve. Well, that's going to take a lot of time. So if we approximate the area under the curve, f of x equals x squared from 1 to 2 by 5 rectangles, we're going to use rectangles with equal bases and the heights equal to the height of the curve at the left-hand edge of the rectangles. Okay, so what we're going to do, we're taking this curve, f of x equals x squared. If you recall from algebra, that's a parabola. Okay, but we're only going to go from 1 to 2. So this area here. So not a lot, not the whole area, just part of it. And we're going to take that part and divide it into 5 different rectangles that have an equal distance from 1 to 2. Well, to find that, to figure out what that change, what that base needs to be, we're going to take our beginning and our end point from 2 to 1. So we'll do 2 minus 1 on the top, and we're dividing it into 5 rectangles. So this tells us that each base of our rectangle needs to be 0.2. If you look at this next slide, So along the x-axis, we start at 1, and we draw a rectangle that goes from 1 to 1.2, and connect it up and over. Then we're going to go from 1.2 to 1.4, and again go up till we hit the curve, connect over. And then 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. Now, remember, finding area of a curve, or not a curve, a rectangle. So for the rectangle, area equals base times height. Well, the base we had, it's 0.2. The height, okay, is from the x-axis up to the curve. Well, that's going to be whatever our function is. Okay, so that's our x squared. So it'll be 1 or 1.2 or 1.4 or 1.6 or 1.8. Okay? And once you find the area of each of these individual rectangles, you can then add them together and you have an approximation. So that's what we have. The height of from say 1.4 to 1.6 is 0.392. Okay. The next slide here shows all those areas. Okay, showing just like I showed you above how to find the area. And we get an approximation of 2.04. So approximately that's how many square units are underneath that curve, if we're approximating with 5 rectangles. Well, what would happen if we had more rectangles? Well, calculating by hand would become very tedious. Okay, say I had 50 rectangles here. That would be a very tedious process to go through. But, let's see. As we saw earlier, using only 5 rectangles does not give a very accurate approximation for the true area under the curve. So if we wanted greater accuracy, we use more rectangles. And what this next slide showed, slide 10, we have what the approximation would be if we added more and more rectangles. So they go from our 5, which gave 2.04, that from our first example, all the way up to 10,000 different rectangles. And we get an approximation of 2.33. And you can tell once you got from 100 down to 10,000, those numbers are getting closer and closer together. So as the numbers get closer and closer together, we see that we actually have a more true representation to what the area under that curve is. So the areas in the right-hand column are approaching 2.333, or 2 1/3. That is the exact area under the curve of f of x equals x squared from 1 to 2. It's 2 1/3. So what we have is, or how we could find this in the process for finding these, is what we call the Riemann sum. Okay, so approximating the area under a non-negative function. Okay, so this works when your curve is above the x-axis. When they say non-negative function, our curve is above the x-axis. We're going to find rectangles. Okay, so if you're finding it using this approximation, you would find what width you need your rectangles to be, find all the x values that you need, and then calculate all those individual areas. Okay, the Riemann sum. But that's going to take a very long time, and it's very, very tedious. So we have a better way. We have a faster way. And that's where we get to use our integrals. The limit of the Riemann sum as the number n of rectangles approaches infinity gives the area under the curve. All right? And that is called the definite integral of a function from a to b. And it's written as the integral from a to b f of x dx. Okay, so I'm going to zoom in right here. So the definition of the definite integral, we read the integral from a to b of f of x dx. Okay, that's how we read that. It says, let f be a continuous function on an interval a to b, the definite integral of f from a to b is defined as the limit of the Riemann sum. Okay, the limit as n approaches infinity. And again, this part here would be very, very tedious to do by hand, but if we use the rules of integrals that we've already learned in the first two sections, this becomes very, very fast. Okay, the numbers a and b in our integration are called the lower and upper limits of integration. Okay, so when you see that phrase, lower and upper limits of integration, that's the a and b. That's the beginning x value and the ending x value for your function, wherever we want to find the area under. All right, let's keep going. So how do we deal with that now? It says a function followed by a vertical bar with numbers a and b means evaluate the function at the upper number b and then subtract the evaluation at the lower number f. So f of x evaluated from a to b is how you would say this. When we write this as a function, so say I had 2x evaluated from 1 to 3. That means I need to plug 3 into my function, so 2 times 3, and then subtract, plugging 1 into my function, 2 times 1. We can evaluate that. 6 minus 2 is 4. Okay. Again, this bar means evaluated from a to b. And we're always going to subtract the upper limit from the lower limit. So I want you to pause the video and try example 2. Evaluate both of these functions using the upper limit minus the lower limit. All right, so from the first one, x squared evaluated from 3 to 5, you would have 5 squared minus 3 squared, which gives us 25 minus 9, which is 16. On the second one, the square root of x evaluated from 4 to 25 gives us the square root of 25 minus the square root of 4 equals 5 minus 2, giving us an answer of 3. All right, we're going to use this in the next video to show how do we actually go about evaluating an integral.